Welcome to Brain Vision.
So for this problem, we will consider the system as follows. And for part A, we will locate the instantaneous center corresponding to the center of percussion P. We'll let dP equal to the distance gP between the mass center and the center of percussion line. So initially we have the system at rest, so it has no momentum. Then we have an impulse, F delta t, acting along the center of percussion. And finally, we have the mass center of the system moving with momentum m v bar and rotating with I omega, which is its angular momentum. So for part A, the first thing we'll do is find the components parallel to F delta t. F delta t is along the center of percussion. So these components are 0 initially. We're using the conservation of impulse and momentum here, plus F delta t, which is the only impulse in the direction. And finally, we have the momentum of the mass center, which is m v bar. And next we look at the moments about the mass center G. So the moments about G, initially we have 0, plus at the point of impulse, we have Gp, distance Gp, we call dP, times this impulse, F delta t, and this is equal to the final moment, the angular momentum, is I bar, the center of the moment of inertia, times the angular speed at which the rigid object is now rotating, omega. So essentially we have two equations, and we have F delta t in both of these equations. So if we eliminate F delta t in each of these equations, we get that V bar over omega. So F delta t is essentially mv bar. If we put mv bar into the second equation, we get v bar over omega is equal to I bar over m dp. So we can rewrite this I over m dp as k bar squared, the radius of gyration, over dp. Since we know that I bar is equal to m k bar squared. That's the definition of mass center of mass moment of inertia. Now we redraw our diagram and we locate point C. So here we have our mass center moving with velocity v bar, mass center of our rigid object. Rotational speed is omega, and our instantaneous center, which we wish to find, point C, is a distance. So instead of saying GC, we'll call this DC. So that just simplifies our equations a bit. So we'll call that distance GC D subscript C. So now we wish to locate point C. So GC, which we've called D subscript C, is equal to V bar over omega, and this is K bar squared over dP. So GC is equal to K bar squared over GP as required. So we've located point C, the instantaneous center, with relation to the center of percussion, point P. So GC as required is K bar squared over GP. Now, for part B, we will do the same. However, this time we will place the center of percussion P prime at point C. So the center of percussion P is the instantaneous center C. We need to calculate the corresponding instantaneous center C prime. So from here we can see again initially our system's at rest before an impulse F delta t acts along the old center C, which is the line of percussion P prime. The distance we will call between P and P prime and G, we will call dP prime, again just to make things easier. And then this is equal to our mass center moving off with momentum mv prime and rotation with angular momentum I omega prime. So again, we're going to use the conservation of momentum and impulse. So we can also see from here that dP prime so that's dP, and the prime is for the P, it's the distance of P prime from G. dP prime is equal to the distance from G to P prime, and this is the same as GC since the center of percussion lies at the instantaneous center GC, and this is equal to D subscript C as we've labeled it in part A. So now the momenta, the system's momenta initially plus the system's external impulse is equal to the momenta of the particles after. So again, we're using the conservation of momentum here. And we'll do what we did above. For part A, we'll first take the components that are parallel to F delta t. So initially, when the system's at rest, that's 0 plus F delta t is equal to mv bar. So mv bar is the momentum of the system. Finally, then we'll again do the moments about the mass center G. So we take moments about G. We get 0 plus d p prime into F delta t is equal to the center moment of inertia I bar times omega prime. So again, like we did before, we have two equations and we have F delta t is equal to mv bar. We'll substitute F delta t is equal to mv bar into the second equation, and we get that v bar over omega prime is equal to I bar over m dp prime. And like before, we show that this is equal to k bar squared over dp prime. And now in this problem, we need to find point C prime. So let's look at our diagram like before. So we have point G at the center moving with velocity v prime or v bar prime. And then we have our instantaneous center C prime, a distance of, we'll call it dC prime from the mass center. And we also have the angular rotation omega prime. So we need to find point C prime like we did before. So what we can see is that GC prime, we've called it DC prime, is equal to V bar over omega prime. And from above, this is K bar squared over dP prime, which is K bar squared over dC. So since we know that dC is equal to dP prime, and we get K bar squared over dC, we also have that remember we have that dC is the same as dP prime in that from part A, we know that this is K bar squared over dP. So this implies that in fact dC prime is actually equal to dP, or that the distance GC prime is the same as the distance GP. So the line GC prime is equal to the line GP. And therefore, our new instantaneous center, C prime, coincides with our center of percussion, which is point P, which is the result as required.